You can see the recording of the lecture here on the G+ page as usual, and here's a scan of the pages. So we'll just quickly look at what we did last time, which was some numerical investigation, some examples of linear congruences. So we're looking at congruences now which are of the form A times X is congruent to B modulo something. So just these degree 1 polynomials, so something times X in a constant term. And we want to understand completely, and you will understand it, or we'll have seen the results that describe it completely by the end of this session here. We more or less saw all the features of it with these examples last time. Okay, so our first example was to look at a linear congruence which had no solutions at all. So even the simple one, 2 times X being congruent to 3 modulo 4. Okay, 4 is a tiny modulus. There's only 4 possibilities for X. You can check them all. None of them work out. So that has no solutions. Okay, so sometimes congruences, polynomial congruences, can have no solutions. Our second example showed that other times they can have lots of solutions. So this wasn't a linear congruence. This is a degree 2 congruence. X squared minus 1 is congruent to 0 modulo 8. Again, 8 is pretty small modulus. There's only 8 possibilities for X. We can check them all, and we see that 4 of them give solutions to this. Okay, so 4 of them give solutions to X squared minus 1 being congruent to 0. 1, 3, 5, and 7. So some congruences have no solutions, some congruences have lots of solutions, more than the degree of the polynomial. Okay. That's something different to polynomial equations. So then we focused on linear congruences. And the first case we looked at was special case. I mean, surely these kind of equations are simple to solve. A times X equals B, simple to solve it, you just divide across by A. X is equal to B divided by A. That's how you would solve it if these were just numbers. And this is the operation, this is the relation of equality here. But of course it isn't, these are congruences. And really these objects here are congruence classes, because we're doing modular arithmetic. Now that thinking is still okay as long as you're talking about something that exists. So when you say divide across by A, really what you mean is you're multiplying across by the object A inverse. As long as A inverse exists, that reasoning is perfectly fine, and indeed the solution is X equal to B times A inverse. Okay? But you need to know that A inverse exists. Okay? You can't talk about things that don't exist. You can't use things that don't exist. You can talk about them, but you can't do anything with them. So will A have an inverse modulo n? Well, we understand the theory of that completely. Whenever A is co-prime to n, so whenever they have a greatest common divisor equal to 1, then A inverse will exist. Simple test. So if we're faced with one of these, we can check A, check that it's co-prime to n. If it is, it will have an inverse, and then straight away we get a solution. There's one unique solution to this linear congruence. So the solution represented by X equals B times A inverse. Okay, so I think we did a quick example of that. 4X being congruent to 7 modulo 15. 4 is indeed co-prime of 15, so it does have an inverse. It happens to be its own inverse. 4 times 4 is 16. Coincidence that 4 is its own inverse. Typically, it will be another number, modulo 15. But 4 is its own inverse, so if we multiply both sides by 4, we have 4 inverse, 4 times 4, so that gives 1. So I put X on the left-hand side. 4 by 7 gives 28, or typically we represent that as 13 modulo 15, or minus 2. Okay? So there's a unique solution to this linear congruence, and it's the congruence class of 13 modulo 15. Okay. So that's fine. We've pretty much covered the theory of such things there when A is co-prime to the modulus. So there's a theorem coming up in a moment, which just basically sets that out in general, and we'll go pretty quickly to the arguments for that. Was that okay? Any queries about this case where the A is co-prime to M. Is there anything I could clear up about it? Okay. So then last time, okay. Sometimes fall into the trap of just giving the previous lecture in my summary. But we then looked at some cases where the A is not co-prime to M. Okay. So this is the slightly trickier case. There's two here. See if I can fit them both on the page. So we looked at two. We looked at a 6x congruent to 7 modulo 15. So 6 is not co-prime to 15. We've got a greatest common divisor of 3. You cannot divide across by 6 here. There's nothing that, there is no 6 inverse here to divide across by, or to multiply across by. And another example of 6x being congruent to 9. There's two types of behavior being displayed here. First case is where there are no solutions at all. Because if we assume for a moment that there was a solution x to this first one, just using the definition of congruence and divisibility, really it puts us in this kind of situation. If there was a solution x, then there would be a linear combination of 6 and 15, which gave us 7. Linear combinations of two numbers, any linear combination of 6 and 15 has to be divisible by the greatest common divisor of 6. Okay, because 3 divides into 6 and 3 divides into. But we know 3 does not divide those. Okay. So there cannot exist an x in the cube. If there is, you'd be forced to accept that 3 divides into 7, but it doesn't. So there cannot exist an x in the cube. So there are no solutions to this linear congruence. But sometimes there can be. And you can kind of explain that the reason there's no solutions is because the greatest common divisor of 6 and 15, namely 3, does not divide into 7. Okay. But here's a case where it does. Greatest common divisor of 6 and 15 does divide into 9. And maybe there will be solutions to this. And indeed there are. Here's the original equation. You can, well, there's a few ways of approaching this, but what we did was we used the definition of congruence, used the definition of divisibility, then we divided across by 3, dividing across by the greatest common divisor, which you can do now because it does divide 9. You get this one, 2x minus 3 equals 5r. So really what you're looking at is 2x being congruent to 3 modulo 5. And then because we've removed the greatest common divisor from the thing, this coefficient that's sitting here now is co-prime to the modulus. Okay? It wasn't before. The 6 was not co-prime to 15, but we divided across by the common divisor. So what's left behind is a co-prime pair. So the 2 is co-prime to 5. So 2 has an inverse, happens to be 3. 2 times 3 is 6. So you multiply both sides by 3. You get x congruent to 9, or equivalently 4. Okay, so x congruent to 4 modulo 5. Just a couple of things to point out. This one, 6x congruent to 9 modulo 15, if and only if x is congruent to 4 modulo 5. So it does have solutions. Anything congruent to 4 modulo 5 is a solution of this congruence. But now, because the original congruence was quoted in terms of 15, we'd like to return the solutions as congruence classes modulo 15. Okay? We'd like to report the solutions of this in the original context. And the original context was talking about congruence classes modulo 15. But now we've got the solution here as congruence classes modulo 5. But congruence classes modulo 5, I mean, here's the congruence class of everything congruent to 4 modulo 5. But within that, there are 3 congruence classes modulo 15. Okay? Because this is equivalent to saying x is congruent to 4. If you look at different representatives from here, 4 is one representative. If you add 5, you get another representative, 9. And add 5 again, you get another representative, 4. So these are all, they're different integer representations of this congruence class. Okay? So these are all congruent to each other modulo 5, but they are different modulo 15. There's only 3 of them because 5 divides into 15 and gives you 3 times. So there are 3 congruence classes modulo 15 within the congruence class of 4 modulo 5. And that's the ones represented by 4, 9, and 14. If you add 5, you don't get a new congruence class. If you add 5 to 14, you get 19. But 19 modulo 15 is congruent to 4. So you just get this solution again. Okay. So really, we report that there are 3 distinct solutions to this, to the 6x congruent to 9 modulo 15. 3 distinct solutions. The congruence classes of 4, 9, and 14 modulo 15. Okay. These 3 solutions, modulo 15, are the solutions to that original congruence. Or that's covered by saying you just got this single congruence class modulo 5. Okay. But we prefer to report it modulo 15 since that was how the original problem was asked. And within this example, we more or less see all the features of the general case. Okay. So when the greatest common, so when the coefficient is not coprime to the modulus, you have to think about the greatest common divisor of the 2. If it does divide the constant in the polynomial, then there will be solutions which you can find a description of by dividing through by the common divisor. Then you're left with a coprime case. So there is an inverse to this. You multiply across by the inverse, you get a description of the solution. But to recover the description of the solution in the original context, you look at multiple representatives of this one to find the different congruence classes modulo the original. And how many distinct solutions did we find here? We found 3 distinct solutions. And that 3 comes from the greatest common divisor. The greatest common divisor of 6 and 15 being 3. Okay, so that greatest common divisor of 3 is the same as this 1, 2, 3 different solutions to the original problem. So is there any questions about that? Yeah.
Second question there.
Yeah.
How do we get a 4?
Well, the 4 came out here, x being congruent to 4 modulo 5. So we start off with 6x congruent to 9 modulo 15. You can then say that you can divide across by 3. This is equivalent to 2x being congruent to 3 modulo 5. And then 2 is invertible modulo 5. That's an inverse of 3.
Divided by 3.
So multiply both sides by 3. You can say you could say divide both sides by 2, and that's the same as multiplying both sides by 3 because 3 is the inverse. 2 inverse is 3 modulo 5. The inverse of 2 modulo 5 is 3. So you multiply both sides by 3, get x congruent to 3 by 3, 9. But the canonical way to say that is x congruent to 4, because you're talking about modulo 5. So these two examples kind of display all the features. If the greatest common divisor of 6 and 15 does not divide the 7, there are no solutions. But when the greatest common divisor does divide the constant term, there are solutions. There's multiple solutions. And the number of different solutions is the same as the greatest common divisor. Okay. Any other queries on that? Okay. So when you look back to the notes then, the theorems are just proving those facts in general. Okay. So theorem 6.1, and we've there isn't really much more to the proofs other than just setting these matters out in general. So theorem 6.1 deals with the case where the A is coprime to the modulus. So you're looking at AX being congruent to B. If A is coprime to N, then there is an inverse. So multiply both sides by the inverse, you get X is congruent to A inverse times B. Now I presented A inverse there in terms of the Euler-Toshin function. Okay. So remember, this was a result called Fermat's little theorem. From the previous chapter, which said if the greatest common divisor of A and N is 1, then A inverse exists and it's congruent to A to the power of phi of N minus 1. The Euler-Toscan function of N minus 1 modulo N. Okay. But the point is, the inverse does exist. So you multiply both sides by it, you get X is equal to the inverse of A times. So one unique solution modulo N. That's basically, I mean, there really isn't, proving it is just kind of saying everything we've just said over and over again. Okay. Fermat's little theorem, or Euler's, this thing has multiple names. Euler's theorem. Maybe Fermat's little theorem maybe only refers to the case where the n is a prime, I think, maybe. So, never quite sure what it's supposed to be called. Okay. So that's all there is. So if A is co-prime to N, the inverse exists, so multiply both sides of it. Multiplying both sides of AX equals B by the inverse, we get X is congruent to inverse times B. We'll now look at theorem 6.2. So theorem 6.2, so we've got two theorems here, 6.2 and 6.3, to describe the case where A is not co-prime to N. So here we have the GCD of A and N being D, some number D. And now this one is just talking about the existence of the solutions. The next result talks about the solutions in detail and how many of them there are. This one just talks about whether or not solutions exist. And it's if and only if D, which is the greatest common divisor of A and N, whether or not that divides B. That determines whether there are solutions. Okay. So this is, in the example we're looking at, this is just exactly the issue of whether 3 divides 7 here, which it does not, there's no solutions, and whether 3, that's the greatest common divisor of 6 and 15, whether that divides 9, it does, so solutions exist. Okay. So we're just doing the general presentation of that and coming up with a general argument for it. It's easy to see why and why not when we're just looking at that specific example, 6x congruent to 9 modulo 15. But now we want to present it in general. So this is going to have to make use of the definition of congruence in terms of divisibility, and maybe the definition of divisibility in terms of existence of the quotient, etc. Okay. So it's an if and only if result. So the simplest way of setting out the proof is to prove both directions separately. Yeah. Assume D does divide B, prove solutions exist. Then assume D does not divide B, and prove solutions do not exist. Except, just seeing it now, let me do it slightly differently. Yeah, here we do the two directions. So we start off by saying solutions exist. So we assume that solutions exist, so that there is an X such that AX is congruent to B. So this is now no longer a question, it's a statement. There is an X such that AX is congruent. Well, congruent means that N divides the difference. N divides AX minus B. You know, unraveling definitions here. Definition of divisibility means there exists a Q, exists a quotient Q such that AX minus B is Q times A. And then what do we have? We have, what this is really, is a linear combination of A and N, which gives you B. So we're assuming solutions exist, and then we get the existence of Q. So here's a linear combination which exists under the assumptions at play at the moment. A linear combination of A and N, which gives you B. But then facts we already know about divisibility then say that any common divisor of A and N, any number that divides both A and N, well, it has to divide B as well. It's going to divide the right-hand side. The right-hand side is a linear combination of A and N, so it must divide the left-hand side. Okay? So that's one direction of the proof. If solutions exist, D, the greatest common divisor of A and N, does divide B, constant term in the congruence. The other direction is to now assume that D divides B. And then the conclusion you're going to have to work towards is that solutions exist. What we want to do, I mean, it was easy to see in the specific numeric example, 6x congruent to 9 modulo 15. We could construct the solution. Well, here we want to describe it in general. Again, it just works with the same thing. Works with the definition of congruence in terms of divisibility, the definition of divisibility in terms of existence of quotients and so on. So what are we assuming? We're assuming that D divides B. You want to unravel that assumption. Work with it. If you're assuming that D divides B, what you're assuming really is the existence of another integer, B prime, which is the complementary factor. So B is equal to B prime times D. So here we see D dividing B, and we've also got a name for the other factor. So B is the product of B prime and D. And we're trying to construct a solution. So the solution is probably going to involve in its construction this number B prime. Again, we call back to the Euclidean algorithm, or equivalently the existence of these linear combinations. Because D is defined as the greatest common divisor of A and N, we know it's possible to write D as a linear combination. And why are we choosing this? Well, you see, we're trying to get a statement about congruence classes modulo N. So starting with the linear combination involving N gets you in the right direction. Because when you've got a linear combination involving N, well, then we know that these two items here are congruent to one another, modulo N, because their difference is a multiple of N. So having linear combinations involving N is a good stepping stone to constructing congruence classes modulo N. So here's a linear combination featuring our D. Now we want to talk about congruence classes of B. We want to construct an X which, when you multiply it by A, gives you the congruence class of B modulo N. And we're staring at a linear combination involving N here and A, usefully, which gives you D. But really, we'd like it to be B. But we can construct that by multiplying both sides of it by this number B prime. When you multiply the left-hand side by B prime, it turns into B. Multiply the right-hand side by B prime, well, you just stick it in there as a factor. And then you do a little bit of reorganization. And here you've got your A here as well. So now you move this to the other side. You see that A times this number. I'm not particularly interested in this. Well, I'm kind of interested in the structure of it, but for now I'm just mainly interested in the fact that this number exists. It's constructed out of R and B prime, which are things whose existence comes from assumptions we've made. So A times something minus B is a multiple of N. So this shows that these two objects here are congruent modulo N. Their difference is divisible by N. So all the time we're moving through the definitions, from definition of congruence back to divisibility. So in other words, N divides the difference, which in turn means that these two are congruent. So here's A times something congruent to B modulo N. So this something is your X. We've shown that the X exists. Solution exists. So that's the second half of that if and only if proof. If D divides B, here's where we assumed it, then solutions exist. Okay. Now, in something like this, you kind of think, well, maybe there's only one solution, because the solution has to look like that. The solution has to be R B prime. B prime is unique. B prime is equal to B divided by D. It's a unique integer, B divided by D. But the R, is the R unique? Because if it was, that means there's only one solution. Well, where did the R come from? The R came from, it was a coefficient in this linear combination. Now we know that those coefficients aren't unique. Okay? Whenever you have a linear combination of two numbers equal to this number over here, there's an infinite number of choices of pairs of coefficients R and S to give you that linear combination. So the R is by no means unique. So this solution X, all we've done is we've just shown that it exists here because the R exists, but there are multiple different choices for R. There's potentially multiple different congruence classes modulo n that we could construct here. This theorem only claimed existence, so we just have to point to one of them. The next theorem, 6.3, deals with the exact number of solutions. So this is talking in general, like we did here in this example, where we found that 3 different solutions modulo 15. But any questions or queries about this one so far? Okay, what I'd like to do then is just look at the statement of the next result. I'll postpone the proof of it. I'll leave you to read through the proof of it yourselves. It's slightly longer than the ones we just looked at, but it's no more difficult. Slightly longer, so a little bit more difficult to read through, but the concepts it's using are just exactly these. Just careful unraveling of the definition of congruence and careful stepping between various divisibility statements and linear combinations. Okay. Well, let's just look at the proof of it. Sorry, at the statement of it. And the statement of it is just the general statement of everything that we saw in this example here. So it's good that I've got them both up here on the board. We can compare one to the other. Okay. But for the benefit of the recording, I'm just comparing the statement of theorem 6.3 to this example here, 6x congruent to 9 modulo 15. Right. Okay, let's go. Here's our general linear congruence, ax congruent to b modulo n. We're assuming that solutions exist. From the previous result, that means we're assuming that whatever the greatest common divisor of a and n is, it divides the constant term b. Okay, so there are solutions, as we know from the previous theorem. So the question is, well, how many of them are there exactly? Well, the theorem claims that it has exactly d solutions modulo n. So there's d different congruence classes modulo n, which you can put in here for x. Just as we found 3 different solutions here. 3 was the greatest common divisor of 6 and 15. 3 divides 9. So this theorem is saying there are 3 different solutions modulo 15, which indeed are the ones we found. And then it just describes them in general. These solutions, these d different solutions, they're the congruence classes of these integers here, modulo n. This looks a bit confusing at first look, but it's t plus I times n over d. So n over d, in the language of this example here, was 5. It was the original modulus divided by the greatest common divisor, so 15 divided by 3. So n over d is 5, in this example is 5. So it's just saying it's t plus every multiple of 5 you get, and the multiples you take are 0 up to d minus 1. Now what is the t? T is the unique solution, modulo n over d, of the reduced congruence, so the congruence where you divide it through by d. There's a lot of symbols there going on, but really, this modulus, this congruence down here, a over dx, congruent to b over d, modulo n over d, that is just this one here, 2x congruent to 3 modulo 5. Congruence you get from the original one by dividing through by the greatest common divisor. Okay? So it looks complicated in general, but you know it's quite straightforward when you compare it to the example. The original congruence, all the parts are divisible by the greatest common divisor of these two. So you divide across, you get this reduced congruence. Now the coefficient is co-prime to the new modulus, so it has a unique solution. So this 4 is t. So that 4 there is this t. So your description of all the solutions is just x is congruent to t modulo n over d, modulo the reduced modulus. But you want to report your solutions with reference to the original modulus. Okay. So these numbers here, t plus I n over d, these are the 4, the 9, and the 14. Because you've got t plus 0 times n over d, and the n over d here is 5. And then you've got t plus 1 times 5, and then t plus 2 times 5. So the 4, the 9, and the 14 are these numbers here. I equals 0, you get 4. I equals 1, you get 9. I equals 2, you get 15. 2 is the last case you take, because that's the d minus 1. If you did take another multiple of 5 on, it would still be a solution. T plus 15, 4 plus 15 being 19, but all you're doing is just naming this solution again. All you're doing is generating 19, which is, we've already listed that solution. We've already said 4 modulo 15. So that there is just a general statement of everything that we see in this example here. Okay. So let's look. The best thing to do is just to see another few examples. So skip over the proof. Proof is just justifying everything in general. You can see the elements used there: congruence statements, transferring to divisibility statements, careful argument of all of them. So let's jump into these examples here. 5x congruent to 3 modulo 24, and 25x congruent to 15 modulo 120. I'll do whiteboard or visualizer. So let's write them down first. 5x congruent to 3 modulo 24. And 25x congruent to 15 modulo 120. Okay, well, why don't you get started, and we'll talk to the solutions in a few moments. So you're looking to solve these two. You've got all the ammunition you need, all the tools you need above. And we'll step through the arguments on the board shortly. If you've got any queries, just ask. Discuss it with your neighbors and so on. Give you 2 or 3 minutes for these, and then we'll talk through the solutions together. We'll get back to them. Oh God, it is. That's weird, isn't it? Must be a setting somewhere. Yeah. Which setting would that be? Stop distracting you with my. Nope, not that. Probably means the lecture I recorded the other day was back to front as well. Okay, I can't find the setting in it to flip it around. So, what did we find? Any solutions to the first one? Yeah, what are they? Or how did you go about solving 5x congruent to 3 modulo 24? Yeah, so see 5 and 24 are co-prime, so there is an inverse. What is the inverse of it? 5. Yeah. So we notice that 5 inverse, again, it's another self-inverse example. Typically things aren't self-inverse, of course, but happens to be again. So this one is equivalent to saying x is congruent to 5 times 3 modulo 24. Multiplying both sides by the inverse of 5. Or in other words, 50. Okay, so really short and sweet. There is a solution, there's a unique solution, modulo 24. Of course, there's an infinite number of integers. You can put in here any integer congruent to 15 modulo 24. So x equals the integer 15, x equals minus 9. 5 times minus 9 is minus 45. Minus 45, if you subtract 3 from it, you get minus 48. Minus 48 is indeed congruent to 0 modulo 24. So infinite number of integer solutions, x, but a unique congruence class, modulo 24 solution to it. Anything congruent to 15. This one, okay, 25 is not co-prime to 120. Okay, so 120 is divisible by 5.